Hi, my name is Mary Dussault, and on behalf of the team that supports the MicroObservatory Robotic Telescope Network, I want to talk to you about some practical strategies and lessons we've learned over more than 2 decades related to broadening participation in remote observing. One of the key motivators, I think, for all of us behind using automated telescopes for education is that it transforms astronomy learning from learning about astronomy to doing astronomy. That idea of integrating the teaching and learning of science content with science practice, or what we often refer to as authentic inquiry. I'll have more to say about that term later. At any rate, everyone involved in remote observing is involved in designing and implementing some combination of hardware, software, and what I call humanware. So I'm going to speak to you about some lessons we've learned across these 3 arenas that can be used to broaden participation in remote observing. So I want to note about the term broadening participation. I'm going to use that in 2 senses. First, the simple idea of scaling participation. How do we engage lots more people in using robotic telescopes to engage with STEM learning? But more specifically, how do we increase the participation of people historically underrepresented in STEM pursuits? So my agenda in 4 parts is first to take note of some strategies from the general education research literature, as well as from our own MicroObservatory practice about what works in promoting positive learning outcomes. Second, I'll identify some promising tools and techniques, our own and others. And finally, I'll close out by issuing a call to action for what we should do next to address the fact that the promise of remote observing really has not yet been met. Okay, so what works? Well, one of the intractable challenges of increasing access to remote astronomy is that the activation barriers are so high. There's so much tacit knowledge involved, even in just looking at the sky, much less using an instrument at the other end of a computer screen to collect digital data that you then have to import into some software analysis tool to make sense of. Our MicroObservatory team has made some particular design choices to prioritize optimizing access at scale and optimizing usability and sense making for novice astronomy learners. So to do this, our Observing with NASA interface, for example, provides complete newcomers to astronomy a really easy on-demand way of getting data every single night. There's about 60 objects that people can take images of. And if 10,000 people ask for an image of the moon, we don't take 10,000 images, but we take 1 image and send it to 10,000 people. So that's our way of scaling and engaging more people. And also the design of the interface tries to help scaffold people through the steps of selecting an object and making choices for the telescope settings. Now, some strategies from the education literature. I want to call your attention particularly to a report from Ruth Krumhansel and all at EDC called Visualizing Oceans of Data. It's a great, really informative report to think about the design of educational interfaces to participatory data experiences, which we're all involved in some way. And so a couple of general principles from the cognitive sciences. One is thinking about how to adjust cognitive load. That is, what are all the ways you can ensure that a learner doesn't have to engage with more information than they can actively process at one time? And how do you really minimize jargon, design the presentation of materials so that over time, at any given time, the learner is paying attention to the germane ideas needed in the moment. And then the second principle from the cognitive sciences is bridging the gap from novice to expert. That is, how can you scaffold the learning experience? And that can be using people, your facilitation strategies, as well as using technology, from video tutorials to curriculum, etc. I think of our solar siblings curriculum from Michael Fitzgerald as being a real example of scaffolding the gap from novice to expert. Now I want to mention some key findings from a National Science Foundation supported study of our Youth Astronet program, which is a national online learning community for kids ages 10 to 14, and they're adult facilitators in either out of school or classroom settings. And the community also includes scientists who act as online mentors. So the Youth Astronet program is pretty flexible. The curriculum has a few essential core elements, but then lots of extension activities that educators can pick from to design their own experience. So this is a pretty dense chart, but essentially it represents the results of regression modeling with the data from 1,200 matched pre and post surveys of participants in Youth Astronet. And in this survey, we asked questions which measured students' astronomy content knowledge, their STEM career interest, their science affinity, the degree to which they like and enjoy science, their computer affinity, and their science identity, that is the degree to which they see themselves as a science person and think other people recognize them as such. So those are our outcome variables. And in addition to asking on both the pre and the post test those same questions, we also asked kids about 34 different instructional experiences and the degree to which they thought that they had experienced that. So things from participating in lots of hands-on activities to interacting with STEM mentors. And so we hypothesized that all of these strategies would support learning outcomes. But in fact, what we found was that really there were two groups of experiences that really supported significant gains in our outcome variables. One was what we call core Astronet implementation, which was the degree to which kids reported using robotic telescopes, working with images, making measurements from images, and asking questions. And then the other group of experiences that resulted in an additional gain in learning outcomes was a group of activities we categorize as making connections, the degree to which students report we made connections between science and art, between science and everyday life. We interacted with STEM mentors. And so students who experienced both those kinds of program features had an additional gain in outcome. Okay. How about some promising tools and techniques from the field for broadening participation? I'm going to talk about three areas: progressions of experiences for learners at different stages, integrating the experience, and expanding the variety of forms of participation. So with regard to scaffolding learners through a progression of experiences, here's an example in the realm of studying exoplanets using robotic telescopes. On the left is our DIY planet search interface, in which allows individuals or groups of learners to analyze a data set of observations of an exoplanet over a night, and actually opens up the black box of photometry by allowing them to see what it means to measure the brightness of a target star in comparison to comparison stars, and to graph that value over the course of a night. So this is kind of a introduction to photometry and variable star measurement, where we would anticipate that the next step for DIY planet search participants might be to participate in the NASA JPL Exoplanet Watch Citizen Science program, in which participants use download software onto their own computer that analyzes lots of images to generate professional light curves to maintain the ephemerides of transiting planets. Another promising technique is integrating the experience from the point where a learner identifies, what am I doing here? What's my purpose, my goal, all the way through making sense of their images and analysis. And here, the thing I want to call our attention to is new browser-based image analysis tools, which I think really help lower the barriers, particularly for classrooms that we know now are all using mobile technology and may not have the greatest bandwidth or storage space. We use JS9, and I want to call your attention especially to the Skynet program out of the University of North Carolina and their Afterglow image processing tool, both of which have been adapted for novice learners. In terms of expanding the variety of forms of participation, this really happens best through collaboration, co-design of experiences with communities. On the right is an image that's part of a program run by the Abbey Museum in Maine that serves Wabanaki youth. And the goal of this program was not to engage kids in using robotic telescopes, but rather to engage them in learning about the cultural star stories from community elders and illustrating those stories with images from the telescope. On the lower left is an example of, from, again, the Skynet program, in which the designers collaborated with blind and visually impaired youth to adapt the image processing tool to sonify data. And I want to play that for you here. And this tool is a great tool. Imagine you're going to see a line going up through the data. Imagine it's a player piano where the keys on the right side are the high pitch when objects appear on the right side of the image. On the left side are low pitched, and extended objects have extended sound. So let's listen. I hope this is loud enough for you to hear. Okay, so finally, I come to my call to action, and I think the last two examples are part of what I want to talk about in terms of we need to broaden our perspective on what it means to broaden participation. And here I'm particularly informed by a report and a set of professional development tools recently developed by Bronwyn Bevan and her colleagues for broadening our perspectives on broadening participation. They were specifically, this report is specifically developed for folks in the museum and science communication field, but I think it's perfectly applicable to all of us in robotic astronomy. And here are some systemic barriers she identifies that might be exacerbating disparities with underrepresented groups rather than mediating new forms of engagement. And so what I want to enlist everyone listening to this talk is to think about what are the ways we can partner with communities, non-dominant communities, to co-design new forms of engagement with robotic observing and to welcome learners and make that participation more likely to result in positive outcomes. So thank you for listening, and I want to thank our sponsors for MicroObservatory, which include the NSF, Smithsonian, and NASA, and also make an acknowledgement that our telescopes and institutions are located on the traditional territories of Indigenous peoples, and invite you to join us in working with communities that have been marginalized by some of the dominant practices of science. Thank you.